Well, thanks for watching this video in which I'm going to start to describe the basics of a concept called angular momentum. And of course you've heard of momentum before if you've progressed this far in a mechanics class. And we now have to refer to that by a different name. We never knew before that there was a different kind of momentum. But the old kind we indicated with the letter P, and it was just equal to the mass of an object times its velocity. We now need to refer to that as linear momentum. And this new quantity is related to it, but we're going to call it angular momentum. Still has the same kind of characteristic. You know, momentum is that quality of motion that really describes most of what's important. In fact, Newton really based everything, the way he described things, by using momentum. So angular momentum is just usually related to like the spin kind of momentum. So here's how we define it. And it's a little unusual because we use the symbol L, either a lowercase l or a capital L. And the fundamental definition actually is in terms of our old familiar linear momentum. So here's how we write it kind of formally. It is a cross product, which you should have seen by now. And what it means is this. If we have an object with some linear momentum, that's mass moving at some velocity. So here I've got an object that's just spinning around and its mass is 200 grams. It has a velocity at this moment of 0.3 meters per second. Then what we do is we cross an r vector with it. Now the r vector means the vector from some axis of rotation about which it's spinning to the location where the momentum is. So in this case, that just happens to be the length of one radius. And a cross product means that you take into account the angle in between the r vector, here my radius, and this velocity vector. Now I don't really need to do that in this situation because that's a 90-degree angle and the sine of 90 is just 1. So what I would do in this case is I would multiply, and I'm going to change everything into MKS units. Notice this is centimeters, so I would call it 0.15 meters. And then my momentum, I'm going to call this 0.2 kilograms. So that times a velocity of 0.3 meters per second is a nice 0.06 kilograms meters per second. And I multiply those together and I have a total angular momentum of 0.0090, listen to these units, kilograms meters squared per second. That's a bit of a mouthful. And what about the direction? Well, the formal way to describe this is to imagine what you get when you cross the r vector with the p vector. That's a right-hand rule. So imagine spinning this radius so that it's pointed in the direction that the velocity is. In this case, we'd have to actually curl our fingers in the kind of counterclockwise direction to make a vector that way point towards that way. And so the thumb indicates which way to describe the direction of the vector. So we would say out of page. You can also just remember that for angular quantities, when you have anything moving counterclockwise, we describe its direction as being out of the page. So that's how we deal with a single object where all the momentum is kind of contained in a nice small little package of mass. But let me show you a little different situation here. What if instead we have a disk, and maybe that disk is the exact same mass and the exact same size as our circularly moving object. Notice it's also 15 centimeters in radius, that would be here. How would we deal with that? Again, if we think of this as L equals R cross P, but the problem with that is, how would we describe the momentum of one little object? I mean, this is just a small little piece of the 200 grams that's moving with this speed. You know, there's a little piece right here in the middle that's not moving at all, and there's pieces all around here that all have different speeds. They all have different directions. They all have different momentum. They could all even have different masses. So really what we need to do is break this up into a bazillion little pieces, figure out all the little masses, all the little speeds, all the little momenta, and then do this cross product and sum them all together. Now you can see what this is turning into. This is the form we call an integral. And after we perform this integral, and I'm not going to do it for you, you could see it done certainly, we usually change the symbol from the lowercase to the uppercase L. This kind of means, well, we have an object where the mass is spread out among, over a lot of space. Well, here's the result of that, and it's actually amazingly simple. You get exactly the same expression that you would get if you just used the moment of inertia times the angular velocity. Remember, the angular velocity is also a directional thing. It's got a vector direction too. Now, what I really like about this is, you see how the two quantities that we use have analogous quantities in linear motion. Moment of inertia has an analogous quantity of mass. I'm just going to jot it over here. And angular velocity has an analogous quantity called velocity. Well, that, of course, is just regular old linear momentum. So these two are a one-for-one corresponding kind of relationship. So I think it makes it a little easier to remember. So now what I need to do is just go about calculating what the moment of inertia for this disk is. And I just know, because I do it a lot, that a disk has a moment of inertia of 1/2 mr squared, its mass times its radius squared. And the angular speed is not given here. However, if I know the velocity of a point on the very edge of this, 1 radius away, then I can substitute in v over that radius, and that'll give me the angular speed for the entire spinning object. So I did this previously. I didn't want you to have to sit through and watch me do all this. Again, I converted my grams and my centimeters into MKS units of kilograms and meters, and I get a moment of inertia of 0.00225 kilograms meters squared, and an angular velocity of 2 radians per second. And so when I multiply those, I get a very nice 0.0045 kilograms meters squared per second. And I want you to notice I've dropped the radians off of here. Radians we don't use if we have other units next to it. So because I have kilograms and meters squared, I would not say the radians along with that. It would just sound kind of odd. So I don't know why I was putting that in parentheses. So there is my value. Again, this would be out of the page. That part of it's no different. And I do want to point out one last thing here before I quit. If you compare that to what we got up here, where we had all the mass concentrated at the very edge of this radius, we got twice the value as when we spread it out among the whole disk. And remember, that's because for each little piece, we have a lot of pieces with a smaller r than what we had out here of 15 centimeters. And so when we kind of add up all the contributions of all those little pieces, it ended up being exactly half of what we would get as what we got when we concentrated it all at one point. So that's how you calculate an angular momentum for both of those situations. And if you want to see what we do with that, a couple more videos involving conservation of angular momentum and other kinds of collisions. Might be worth watching. See you then.